Hi guys, today we're doing GCSE Chemistry, pretty much all the content. Might take a while, but the exam's tomorrow, so it's worth revising. So first we're starting with particles, and there's some summary questions here. If you know them all, then you can move on to the next topic. So first we're going to do the particle model, which is how particles are modeled. So there are three main states of matter. That's solid, liquid, and gas. You can see in the nice diagram here how they look. Solid keeps a Atoms contain protons, neutrons, and electrons. Protons have a charge of +1, a relative mass of 1, and are in the nucleus. Neutrons have no charge, a relative mass of 1 as well, and they're also in the nucleus. Electrons have a charge of -1 and a relative mass of 0.0005, which is negligible, and it orbits the nucleus in shells. Ions are charged particles that have either gained or lost electrons, and isotopes are atoms of the same element of different numbers of neutrons. So that changes the mass and the properties. So that's the end of the first topic. So summary questions. 1. How do particles in different states move differently? Solid particles vibrate slightly, liquid particles flow and collide quite freely and randomly without separating, and gases move freely and they fill the container. What was Thomson's model of the atom? Thomson's model was the plum pudding model, which was a positive sphere with little negative spheres for the electrons. What were the results of Rutherford's experiment? Most particles went through the gold sheet, showing that it was mostly empty. Some were reflected partially, showing that the nucleus was positive and dense enough to deflect them, and some were reflected completely, showing that it had a relatively large mass. What's the difference between an ion and an isotope? An ion has a different amount of electrons from the normal atom. It's lost or gained electrons. And an isotope has a different amount of neutrons from another isotope. So on to the next topic, elements, compounds, and mixtures. So again, there's some questions here. If you know the answers, you can feel free to move on. So chemical formulae. The formula tells you what kind and how many atoms are in a molecule. And the empirical formula tells you a formula in its simplest form. For example, C4H10 will become C2H5 because you've just divided both sides by 2 to get whole numbers. On the periodic table, you're given the mass number and the atomic number of an atom of an element, and the mass number is the protons plus the neutrons. So onto the periodic table, it's organized in groups and periods, which are columns and rows, in order of atomic number. The period tells you the amount of shells the atom has. That's the amount of different set distances that the electrons orbit the atom at. And the group tells you the amount of electrons the atom has in its outer shell, which will tell you how it bonds with other atoms. There are 3 types of bonds that you need to know about. Covalent between non-metals, metallic between metals, and ionic between metals and non-metals. A covalent bond is a shared pair of electrons between 2 atoms. A metallic bond is the electrostatic attraction between positively charged metals, metal ions, and the negative sea of electrons, which is what forms when the delocalized electrons can just flow around. An ionic bond is the electrostatic attraction between oppositely charged ions, which are metals and non-metals. They have opposite charges. So there's some nice diagrams here so you can better understand how they bond. So compounds and mixtures. A substance is composed of one type of molecule or atom. It's pure. A compound is composed of chemically joined atoms or molecules. It's also pure. So a compound can be a kind of substance. Pure substances have one set melting point because they wait for the other atoms in it to melt as well, and that's based on their latent heat. And mixtures melt and boil over a range of temperatures because they're composed of different things with different latent heats. A mixture is not chemically bonded, it's only physically bonded, and it can be separated using physical methods. Filtration is used to separate a liquid and an insoluble solid, such as sand and water. Filter paper is placed in a funnel above a conical flask, and the mixture is poured over the filter paper so that it goes down the funnel into the flask. Since the solid is bigger than the gaps in the filter, it won't go through, but the gaps in the filter are big enough that the liquid can go through, So the residue, the solid residue, is left on the paper, and the filtrate goes into the flask. It's a nice diagram there. There's also crystallization, which is when you have a soluble solid that's been dissolved in a liquid, such as salt and water. So this is to get the solid. You won't get the liquid from this. So first you need to remove any insoluble solids through filtration. Then the liquid is put into an evaporating dish above a Bunsen burner, and it's heated close to the boiling point, but not to the boiling point, otherwise that might damage the crystals formed. Then when like a good amount of the liquid has evaporated off, the solid will form crystals. And there's also simple distillation where you get the soluble solid and the liquid, so you don't just lose the liquid. So the liquid is put in a round bottom flask so that it can be heated evenly by the Bunsen burner. And then the liquid vapor goes into a Liebig condenser, I'm not sure how to pronounce that, and it condenses into a conical flask, and the solid will be left in the round bottom flask while the conical flask has the liquid over it. There's also fractional distillation, which is used for two liquids that have been mixed together, and they have to have different boiling points, otherwise it won't work. So it's the same as simple distillation, except there's a fractionating column over here. So any vapor from the liquid with the higher boiling point will condense and fall back down, and the one with the lower boiling point will fully evaporate, go through the condenser, and then into the conical flask. There's also paper chromatography, which is used to see the components in a mixture of liquids, like in ink usually. So the paper, which is a stationary phase, because that's the one that doesn't move, has a pencil line across the origin over here. It has to be in pencil, because if it's in pen, then that's soluble in water, isn't it? So then you put a small sample of the liquid in it, or the ink in this case, and then the pencil line is just about submerged, but the rest is above the water, so it's all dry and stuff. And the solvent, the liquid, will go up. That's the mobile phase because it's traveling, and it will bring some of that ink up with it, but it will separate it out into its components because it's a mixture, so they'll have different solubilities. You use the RF value to compare it with others. Like if usually you have two samples, and so you can compare how it's moved and what colors separate out. And the formula for RF value is distance traveled by substance over distance traveled by solvent. And it will always be below 1. There's also gas chromatography. I've got a diagram here. Gas chromatography is used to separate compounds and measure the amounts. So the mobile phase is an inert gas that carries the sample. So when the sample is put down here into the hot oven bit, it turns into a gas, and then it's transported through a column by the carrier gas. And then once it reaches the end, it takes different amounts of times to leave the column, and once it's left the column, this gets detected and then sent to a computer, which produces a chromatogram showing when it's left the column. So summary questions. 1. How do you calculate the RF value of a substance in chromatography? It's distance traveled by substance over distance traveled by solvent. What apparatus are needed in fractional distillation? Need a round bottom flask, a thermometer, a fractionated column, a condenser, and a Bunsen burner. What's the empirical formula of C6H12O6, glucose? CH2O. What's the chemical and physical change? I didn't actually go over that. A chemical change creates a new substance and reconfigures the molecules, and a physical change, the particles are just rearranged. When can ions conduct charge? They can conduct charge when they're free to move, so when they're in liquid form or when they're dissolved in water, for example. What is a covalent bond? A covalent bond is a shared pair of electrons between two nonmetals. And what are the stationary and mobile phases of gas chromatography? The stationary phase is silica powder, and the mobile phase is an inert carrier gas, like nitrogen. So onto chemical reactions. So balancing symbol equations. Because of conservation of mass, which is no mass can be destroyed or gained, Unbalanced chemical equations are inaccurate because they imply that mass is being lost or gained. So to balance a chemical equation, you have to change the amount of molecules, but you can't change the amount of little atoms there because that would change the whole molecule, wouldn't it? So for example, CH4 plus O2 creates CO2 plus H2O, and that's unbalanced because it shows that more atoms are being created, like where the two hydrogens go over here. So to balance the equation, use Bottomley's method to turn it into a solvable algebraic equation. So just add coefficients A CH4 plus B O2 plus C CO2 plus D H2O. And from that you get A equals C because they're the same amount of carbons. 4A equals 2D because there's 4 hydrogens here and 2 hydrogens here. And 2B equals 2C because there's 2 oxygens here and 2 oxygens here. And 2B equals C plus D because there's 2 oxygens here and 2 oxygens and another oxygen here. So from that you can solve it, and you can just assign a random number to one of the letters and then solve it from there. Moles. A mole of an atom will have the same weight in grams as the relative atomic mass. For example, a mole of carbon-12 will be 12 grams because the relative atomic mass is 12, so the weight in grams would be 12. And this applies to molecules too. A mole of H2O, which MR is 18, will be 18 grams. The amount of particles in a mole of anything is 6.022 times 10 to the 23. That's Avogadro's constant. Moles are needed in stoichiometry, and the formula relating mass to moles is mass equals mR times moles. I like to remember that as mass equals Mr. Moles. So stoichiometry, I actually did a video on this a little while ago. Stoichiometry is the relationship between weights of products and reactants in a chemical reaction. So given a balanced chemical equation and the value for the mass of a reactant, you would be able to calculate the mass of the other reactants and the products. And you'd need a periodic table to find the relative molecular masses to calculate the moles, or you could just memorize them like I do. So here's a little example. So I've given you the equation CH4 plus 2O2 creates CO2 plus 2H2O, which is balanced, so you can actually do it. I've given you 88 grams of CO2. Well, that's what's been produced. So work out the mass of O2 that I had to start with. So first you can see that there's 2 moles of CO2 because mass over MR, 88 over 44 is 2. So you can see that in the reaction, 2 moles of oxygen react for every 1 mole of CO2 because you see there's 1 mole here and 1 mole here and 2 moles here. So 2 times 2, that's 4 moles of oxygen. So you then use you then find the mass of oxygen using the formula mass equals mR times moles. And 32 times 4 is 128, so the answer would be 128. So exo and endothermic reactions are types of reactions. In a chemical reaction, there's always one side that's exothermic and one side that's endothermic because making bonds releases energy and breaking bonds takes in energy. An exothermic reaction will result in a positive change in temperature, and an endothermic reaction is the opposite. So an endothermic reaction will take in energy and result in a negative change in temperature. So you can see a reaction profile here. There's an activation energy which is needed to start the reaction, and then the products will have less energy in the end. And in an endothermic reaction, the energy starts low and then ends up quite high because it's taken in energy. An example of an exothermic reaction is combustion. That's just a fire or something. So a fire is exothermic. Neutralization is when an acid and a base react to form a water and a salt. The half equation is H plus OH minus creates H2O. H plus is the acid ions and OH minus is the base ions. An acid has a pH below 7 because 7 is neutral. It contains H plus ions, and a strong acid has more of these than a weak acid. A strong acid is completely ionized. A base has a pH above 7, which is neutral, and most contain OH minus, but some don't because there's also the alkali metals, and they all neutralize an acid, and alkali is a soluble base. So these are the reactions to remember. An acid and a base create a salt plus a water. Metal and an acid create a salt and hydrogen. Carbonate and acid create salt and water and carbon dioxide. and an acid and ammonia create an ammonium salt, sorry. Electrolysis is used to break down a substance into ions using electricity. Ions are attracted to the electrode being charged by a DC power supply, which is often a battery, and the ions are either dissolved in water or in molten form so they can move, because ionic compounds, they need to move. So the cation is attracted to the cathode, the cation is just a positive ion, and the anion is attracted to the anode, the anion is the negative ion. So pure substances are produced at each electrode. If the electrolyte is in an aqueous solution, if the cation is more reactive than hydrogen, you've got a reactivity series up here, then hydrogen will form at the cathode because hydrogen will be displaced. So, and if there's no halide ions present, then the oxygen will form at the anode. So reactivity series is the order in which metals are more reactive than the others. So I've got a diagram here. Summary questions. How many particles are in 2 grams of hydrogen? 6.022 times 10 to the 23, that's Avogadro's number. So does an exothermic reaction end with less or more energy? Ends with less energy because it's given out energy. So 3 is in 2 parts. First, balance H2 plus O2 creates H2O. 2H2 plus O2 creates 2H2O. And show me answer the next one for some reason. If you have 32 grams of oxygen in excess hydrogen, what will be the mass of water produced? Use stoichiometry to figure that out, and that will be 36 grams. So what is produced at the cathode in electrolysis of sodium chloride? It's hydrogen because hydrogen is less reactive than sodium, so that will be produced. Identifying reactions and products. So there's properties of elements. Different groups have in a group all the elements will have similar properties. So group 1 is an alkali metals. They're soft with low melting points and low densities. They're very reactive because they have one valence electron, which is the electron on the outer shell. As you go down the group, they'll be more reactive because the electron will be further from the nucleus, so it will be less attracted. Group 7 elements are halogens, and they're all diatomic, which means they're all found as 2 atoms rather than 1. You won't find one halogen on its own. As you go down the group, they'll be less reactive because higher up the group, a halogen has to gain an electron, so it's easier for an electron to be attracted to the nucleus if there's less shells. Group 0 elements are noble gases that are inert because their outer shells are full and they exist as single atoms or gases. There's transition metals, which are the normal stereotypical metals like iron, and they're strong and dense with a high melting point. Some of them can form different charges, for example Fe2 plus and Fe3 plus, that's iron. And they're good conductors of electricity and heat. They're malleable, which means they can bend, and generally not very reactive. Some metals, notably iron, react with water and oxygen to form rust. So that's Fe2O3 with H2O. There's displacement reactions, which are when a more reactive molecule takes the place of a less reactive one. For example, fluorine and sodium chloride will create chlorine plus sodium fluoride because the fluorine is taking the place of the chloride as demonstrated in this diagram here. So with this, you can predict when a displacement reaction will take place, or you also need to know the reactivity series for that. So a quick question, will magnesium react to displace sodium sulfate? No, it won't because sodium is more reactive than magnesium. So there are tests for gas. There are 4 that you need to know about. The test for hydrogen, the test for oxygen, the test for carbon dioxide, and the test for chlorine. For hydrogen, you put a lid splint in a tube of the gas, and a loud pop sound would be produced if there's hydrogen in that tube. For oxygen, you put a glowing splint, like one that's been blown out but is still glowing, in a tube of the gas. And if there's oxygen in that tube, it would relight because oxygen's a fire accelerant. For carbon dioxide, you put the gas through lime water and a white precipitate would form, which is calcium carbonate or limestone, and that will make the water cloudy. And for chlorine, you put damp blue litmus paper in a tube of the gas, and it will be bleached by the chlorine, it will be turned white. So there's cation and anion tests. You can identify a metal ion based on its reaction with sodium hydroxide. Fe2 plus will form a green precipitate, Fe3+ will form a brown precipitate, Cu2+ will form a blue precipitate, and Mg2+ and Al3+ and Ca2+ and Zn2+, they'll all form white precipitates. You can tell the difference between zinc ions and other ones because if you put more sodium hydroxide in, the zinc hydroxide will redissolve, but if you have the other three, then you don't really know, I guess. You can use a flame test for them. Sulfate ions will react with barium chloride to form a white precipitate, so that's how you know if an ion has sulfur in it, or sulfate. Halide ions react with nitric acid and silver nitrate solution, or dilute nitric acid and dilute silver nitrate solution to form different precipitates. Chloride ions will form a white precipitate, bromide ions will form a light yellow, and iodide will form a yellow precipitate. When I did this in real life, it was quite difficult to tell the difference between bromide and iodide, but in theory bromide is lighter. So flame tests are used to identify metal ions again, so you use a clean nichrome wire, which is this little wire over here, and you can clean it with like hydrochloric acid, and you put the unknown metal compound on the wire, then put it on the Bunsen burner and observe what color the flame turns. So if the metal is lithium, then it will turn red. If it's sodium, then it's yellow. If it's potassium, then it turns purple. If it's calcium, then it will also turn red, but lithium is like a nicer red. Calcium is like a orangey red. And copper will turn it a nice, beautiful green. So summary questions. 1. What does a white precipitate formed in lime water indicate? And indicates carbon dioxide. 2. What test is used to identify oxygen? So glow and splint. And 3. What color will potassium cause in a flame test? Or cause purple. And 4. What is barium chloride used to test for sulfate ions? And 5. What color will an iodide ion create when reacted with dilute nitric acid and silver nitrate? It will turn yellow. So monitoring and controlling chemical reactions. So first we've got the molar volume, which is quite simple. At room temperature and pressure, which is the room temperature and pressure in the room, 1 mole of any gas will take up 24 decimeters cubed. Doesn't matter which gas it is, it will take up that amount of volume. So you can use this to calculate the volume occupied by a gas given off as a product of a chemical reaction. Like if the reactants are gases or solids, it's slightly different for them. So first you get the balance symbol equation, and you'll be given either the volume of a gas reactant or the mass of a solid reactant. So the method is slightly different for them. For a gas reactant, it's a bit simple. You can just use the symbol equation to see how many moles of gas are produced for 1 mole of reactant, then multiply that number by your given volume. It's kind of like stoichiometry, and that'll be your answer. For a solid reactant, you'll find out how many moles of the reactant you have using the formula of moles equals mass over mR, then multiply your moles by 24, and that will be your answer. Yield and rate of reaction. The yield is how much useful product is produced from a reaction. A reaction will have a theoretical yield, the amount of product that could be produced based on the balanced equation, like you do some maths to figure that out, and an actual yield, the amount of product that is actually produced. The actual yield will never be higher than the theoretical yield, because then that's just adding atoms in, isn't it? So yield can be reduced when something reacts unexpectedly, so it gives off a different product, when some of the product dissipates, or when it's lost to the surroundings, or if some is stuck to a surface. And there's a nice little formula here. Efficiency equals actual yield over theoretical yield. The rate of reaction is how fast a reaction happens. The rate of reaction can be increased with high temperature because the particles are moving faster, high pressure because the particles are more condensed, use of a catalyst because then there's less activation energy needed, or high concentration, so there's more actual particles. Now we're on to reversible reactions and dynamic equilibrium. A reversible reaction is when the products of a reaction are able to turn back into reactants. A simple equation would look like, well, here's an example, NH2 plus 3H2 creates 2NH3, but that can actually turn back into 3H2 plus N2, and this is actually the reaction in the Haber process. Dynamic equilibrium is when the forward and reverse reactions are occurring at the exact same rate. So this can occur at any position in the reaction, like really far forward or really far back or in the middle. Certain factors will shift the position of the equilibrium. The Chatellier's principle is that equilibrium will shift to counteract any change in the system, so that it doesn't want that change. So if the temperature is increased, then the reaction will go to the endothermic side, so some of that energy is absorbed so that the temperature decreases again. If the pressure is increased in a reaction involving gases, then it will go to the side with the least moles, so that with that molar volume, less moles will mean less volume. So I mean more volume, less pressure. And if more reactants are introduced to one side, then it will shift to the other side to reduce that number. So concentration and titration. Well, this is a long topic. Concentration is measured in grams per decimeter cubed or moles per decimeter cubed. Concentration is how much of a solute is in a solution. You can go between grams per decimeter cubed and moles per decimeter cubed using the formula grams per decimeter cubed equals moles per decimeter cubed times mR. Titration is used to find the concentration of a basic solution, which is one with bases, using a neutralization reaction. You'll need a beaker of an acid with known volume and concentration, phenolphthalein to see accurately when the solution becomes neutral. That only works if the solution is basic. It doesn't work for acids. A white tile to see the color change more clearly. For acid, you'd use methyl orange. And a burette of the basic solution to accurately measure out the volume needed to neutralize the acid. This can also be used to find the concentration of an acidic solution with a basic one. You just reverse it. So how to titrate. I'm so sorry about this slide, it's a bit long. So in this example, I've given you, let's see how long it is there, HCl of an unknown concentration, 2 moles per decimeter of NaOH, and all necessary apparatus. So first you use a pipette to accurately measure out a volume of NaOH, which you measure out 50 cm cubed. Then you put a burette on the stand with HCl up to the highest reading in the burette, which will be 0 centimeter cubed, which is up here. It starts from 0 and then higher numbers lower down the pipette. And you put your beaker on a white tile. The burette has a tap. Put some methyl orange in the beaker and open the tap. I think I might have gotten that wrong. I think you're meant to use phenolphthalein instead of methyl orange. Oh well. So you put that in the beaker and open the tap. Swirl in the solution to make sure it's reacted evenly. You can open the tap fully or partially. Here you open it fully so it goes faster. And when it starts to change color, you close the tap partially so that it goes dropwise until it turns completely colorless. That way you could be way more accurate. And you read the amount of NaOH that you've used. We'll say it's 25 cm cubed. Now convert your volumes to decimeter cubed by dividing it by 1,000, and calculate the moles in the sodium hydroxide. Use the Balance symbol equation to see how many moles of sodium hydroxide would react with a mole of HCl, which is 1. Then you use the formula concentration equals moles over volume. So your answer should be for summary questions. What is the molar volume? Went over this, it's 24 decimeter cubed. What factors affect the rate of reaction? Temperature, pressure, presence of a catalyst, concentration. How does a catalyst affect the overall change in energy? That's a nice little trick question there. It doesn't, it only affects the activation energy. What is the dynamic equilibrium? It's when the forward and backward reactions in a reversible reaction are occurring at the same rate. How will a change in pressure affect the volume, the position of a dynamic equilibrium in a reaction involving gases? It will shift to the side with the least moles. So, global challenges. This is a last topic. Extracting metals. An ore is a mineral with enough of a compound to be extracted for a profit. Unreactive materials can be found in pure metal form, known as a native metal. That's what the metal's called. These are easy to extract because you can just mine them out, but most ores are found as metal oxides or other compounds because they're a bit reactive. Metals less reactive than carbon can be extracted using displacement with carbon. So you get metal oxide and a carbon, and you have to heat that up to get the reaction going. And then that's metal plus carbon dioxide. So that's the pure metal over there. So metals more reactive than carbon will have to be extracted using electrolysis. And there's also phytoextraction, where a plant absorbs small amounts of metal in the soil, and then they burn the plant so they can get that metal. And bioleaching, where little microorganisms, they oxidize the metal so it can be extracted using displacement. The Haber process. The Haber process uses nitrogen and hydrogen to form ammonia, so they get the nitrogen from the air and the hydrogen from some water. It's very useful as fertilizer. The reaction is reversible, so the forward reaction is exothermic, so they have to be compromised on the conditions. Since the forward reaction is exothermic, a higher yield would be produced with a lower temperature, but rate of reaction it will be really slow, so it will be really inefficient. So a high temperature produces a low yield, but it's a lot quicker. So they compromise and use a relatively low temperature of 450 degrees Celsius. Since there are less moles on the right side, which is the forward reaction, an high pressure will produce a higher yield, but will be more expensive. So they use 200 atmospheres, not that high pressure. It's really high pressure. You wouldn't survive that. For higher efficiency, they use an ion catalyst to produce that separate route with lower activation energy. And they also, once ammonia is produced, they take that ammonia out the system so that it doesn't unreact, and then any gas that hasn't reacted, it's recycled back into the system. The contact process is used to produce sulfuric acid, which can be used as a fertilizer, as a catalyst in esterification, which is an ester reaction. So in this process, three reactions happen. S plus O2 creates SO2, and 2SO2 plus O2 is a reversible reaction. It produces 2SO3, and SO3 plus H2O creates H2SO4, which is your sulfuric acid. Like the Arbor process, the forward reaction is exothermic, so to compromise on that, it happens at 450 degrees as well, and high pressure increases the yield, but it's expensive, so 2 atmospheres is used compared to 200. So alloys. Alloys are metal compounds that have more useful properties than the pure metal. So, for example, steel is an alloy of metal and carbon. Alloys are harder than pure metals because they have different sizes of atoms, so it doesn't lose. So it loses that regular structure, and the layers don't slide as easily. You can see in that diagram here, it's really irregular. Some examples of alloys are stainless steel, duralumin, brass, and solder. Corrosion is when a metal breaks down due to chemical reactions. It could be a reaction with an acid, or oxidation, or rusting. This reduces the structural integrity of the metal. One way to stop corrosion is to coat a material in something. For example, cars are painted so the air and water can't get to the steel foundation, can't go through the paint. Another way is to put it together with a more reactive metal, so the more reactive metal corrodes instead, which is sacrificial protection. Now onto the Earth's atmosphere. So nowadays, the Earth's atmosphere is produced of 79% nitrogen, 20% oxygen, 1% argon and water vapor, and 0.04% carbon dioxide. In the past, the atmosphere was mostly carbon dioxide, similar to how the atmosphere of Venus is now. So when the Earth cooled below 100 degrees Celsius, because that's what happens to planets, they cool down, clouds of water vapor that were from the volcanoes, they started to condense and form the oceans. They lay the foundation for anaerobic life forms, and then they turned into algae, which photosynthesized and produced oxygen and takes in carbon dioxide. This carbon dioxide became locked into the algae and the plants and stuff, and the atmosphere became rich in oxygen and led to more life evolving. The greenhouse effect is when greenhouse gases, which are like carbon dioxide and stuff like that, they absorb and re-emit infrared radiation, which is heat, and they prevent it escaping into space. So you can see here that the sun gets heat into the Earth, and then it bounces back off the Earth, but then goes back into the Earth. This helps warm the Earth and sustain life, and increases the average temperature, contributing to global warming. And there's also evidence that human activities increase greenhouse gases, like burning fuels and plastics and stuff. Burning fuels releases pollutant gases like sulfur dioxide from the impurities, and carbon monoxide from incomplete combustion. Crude oil is liquid of dead organisms from millions of years ago, and it's composed of hydrocarbons, mostly alkanes. It's separated using fractional distillation so that the different products can be used individually. The short chain alkanes have lower boiling points, so they go higher, and the long chain alkanes have higher boiling points, so when it gets to below their boiling point, it condenses and falls back down into whatever fraction it belongs to. Alkanes. Oh, by the way, if you're in combined science, that was it. That's all of chemistry. And if you're in triple science, then unfortunately we have a good amount more. So you can click off the video if you're combined science. Do I even have people in combined science watching my videos? Alkenes. They're a hydrocarbon with the general formula CnH2n+2. That's N for amount of carbons and hydrogens, not M for nitrogen. So for example, there's methane, CH4, and they make up a homologous series. They're saturated, meaning that they have the maximum possible amount of hydrogen for the carbon, and they contain only single bonds, so they can have more hydrogens. You can see up here, only single bonds. They're found in crude oil, and when they're burned, they're likely to undergo complete combustion. But longer chain alkenes are less likely to undergo complete combustion. The longer chain alkenes have a high melting point, less volatile, which means they evaporate less easily, and they burn with a smokier flame because of that carbon monoxide being produced. Now there's alkenes, which are a little bit more interesting. So they have a double carbon bond, so they're unsaturated, they don't have all the hydrogens. Their general formula is CnH2n. Again, that's N for amount of carbons and hydrogens, not for nitrogen. And they react with diatomic molecules such as Cl2 to form alkanes. They are obtained through the Kraken reaction, where an alkane is heated using a Bunsen burner, and then it's got a porcelain catalyst, and a thermal decomposition reaction happens. So an alkane produces an alkane plus an alkene. You can tell the difference between an alkene and an alkane with bromine water. If you mix them, an alkene will react with the bromine to turn it colorless, and an alkane won't react with it, so it will stay orange. So alcohols and carboxylic acids. Alcohols contain the functional group OH, and they're formed when an alkene reacts with steam. The general reaction is CnH2n+1 OH, like ethanol, C2H5OH. They can be used as solvent, disinfectant, flame starter. Ethanol can be mixed with things for drinking. Generally, that one's produced from fermentation in it. And carboxylic acids contain the functional group COOH, and they're formed from the oxidation of an alcohol, which is why if you leave an alcohol out, it'll, I don't know, taste sour, won't it? So that's why you don't leave your wine sitting around. There are weak acids, and they're used in the production of polymers. So now on to polymers. Polymers are long chains of molecules called monomers. They're used in plastic and fabrics. There's two types of polymerization reactions. There's an addition polymerization and condensation polymerization. Addition polymerization happens when the molecules are unsaturated and they're all identical. The double carbon bond breaks into a single bond and they join together by the carbons. You can see in this nice little diagram here. Condensation polymerization. Condensation polymerization happens when two different monomers usually with double functional groups, they react together. They form small molecules such as water. Polyesters form when a dicarboxylic acid reacts with a diol. So a dicarboxylic acid has two COOH groups and a diol has two OH groups on either end. So when they react, an ester link is formed, and the water comes from the OH from the dicarboxylic acid from this end, and the H comes from the diol. And I think that's it. Oh, summary question, sorry. So 1, what is the result of the oxidation of ethanol? Ethanoic acid. What are the monomers in polyesters? Dicarboxylic acids and diols. What needed to happen for the formation of the first oceans on Earth? Earth cools below 100 degrees Celsius. What does the contact process produce? Ammonia for fertilizers. And can tin be used as a sacrificial metal for iron? Yup, because it's more reactive than iron. Right, that's it. Bye. Good luck in your exam.